Thank you, Professor. And good morning, everyone. My name is Wen-Jun Deng. I'm from Southeast University in Nanjing, China. It's a really great honor for me to have the opportunity to share my research with you here. And today, my presentation is implementation of FourParameter LC Sensing through Symmetric Dual-Resonant Circuit. And my presentation will include these 4 parts. First of all, I want to introduce you something about the basic theory of LC sensors technology. This is a structure of a typical LC sensor system, which is composed of a readout coil and a sensor chip. The LC sensor consists of an inductor and a sensing capacitor. The resonant frequency of the sensor will be shifted with the sensing capacitor corresponding to parameter we are interested. And there is a magnetic coupling between the readout coil and the sensor inductor, so the resonant frequency of the sensor can be wirelessly detected. LC sensor have many good features. It's passive, wireless, and since there's no battery, it can have a long lifetime. All these features make it very attractive in many applications, like implantable devices for blood pressure and intraocular pressure monitoring, and wearable devices like smart bandage for wound management, and the smart package for medicine and food quality control, and in some complex situations like rotating and high temperature and pressure. There are many parameters we are interested that can be detected using this kind of technology. However, there is still a big challenge for LC sensors, that is the limitation of the detection number. As you can see, a traditional LC sensor have only one resonant frequency, which can be utilized to characterize one parameter of interest. And if we put 2 sensors together to detect different parameters at the same time, the mutual inductance between the readout coil, between the different sensor chips, will cause an interference. So when one sensing capacitor is changed, both resonant frequency will be shifted with it, so which makes the readout signals unstable and unreliable. In order to solve this problem, now we proposed a new method to realize 2 parameters and up to 4 parameters monitoring at the same time. Let's begin with the 2 parameters. This is the dual-resonant circuit we proposed. As you can see, it is composed of 2 fixed inductors, L1 and L2, and 2 fixed capacitors, C1 and C2, and 2 sensing capacitors, Cx and Cy. And using the Kirchhoff's law, the dynamic equations of the circuit can be expressed. When C1 equal to C2 and L1 equal to L2, there are 2 resonant frequencies can be derived. As you can see, when other parameters are fixed, the F1 is only controlled by Cx and F2 is only controlled by Cy. So these 2 resonant frequencies are independent from each other, which make it possible to characterize 2 different parameters at the same time. Then we make a simulation using advanced design system to confirm our theory. As you can see, there are 2 resonant peaks that can be detected from the S11 parameter. And it proves that the simulation resonant frequencies are perfectly match our calculation results. As you can see, when C1 is fixed and C1 is increased, only F1 is decreased with Cx. And similarly, only F2 is decreased with Cy. So one sensing capacitor is changed, only the corresponding resonant frequency will be shifted with it. So what we need to do is just choose a correct sensing capacitor corresponding to different parameters. Then we can monitor different parameters at the same time. And based on the theory, here we designed and fabricated a flexible humidity pressure sensor. As you can see, Cx is an interdigital capacitor with graphene oxide as the moisture sensing material, and the Cy is a pressure-sensitive capacitor with a microstructured PDMS as the dielectric layer. So Cx and Cy are corresponding to humidity and pressure, respectively. And this is a fabrication process. The PDMS dielectric is fabricated using a silicon wafer with arrays of inverted micropyramid as a mold, and all the circuits was fabricated on both sides of a flexible PET substrate using electroplating process. And this is the fabricated sensor and the pressure test. As you can see, the two resonant frequencies can be detected from the S11 signal, which is using a readout coil connected with a network analyzer to detect it. So when the pressure is increased, only F2 is decreased with a sensitivity of 48.5, while F1 is almost stable. And similarly, this is the humidity test. When the relative humidity is increased from 20 to 90, only F1 is decreased with a sensitivity of 67.7, while the deviation of F2 is negligible. So it proves that these two resonant frequencies are independent from each other and can be characterized to different parameters, that is pressure and humidity. So two parameters monitoring is realized. Then how can we monitor 4 parameters at the same time? This is still the resonant circuit we proposed, but the difference is there are two sensing resistors are added. As you can see, Rx is in parallel with Cx, and Ry is in series with Cy. So the two resonant modes of the circuit can be simplified into different equation circuits. The first one is a shunt resonant circuit, and the second one is a series resonant circuit. So different circuits can have different equation inductors and capacitors, and the frequency and quality factor of different modes can be calculated. As you can see, F1 is still controlled by Cx, and Q1 is only controlled by Cx and Rx. So we can use the frequency to corresponding to the sensing capacitor, and using the quality factor to characterize the sensing resistors. And that is the same for the second resonant mode. So, and the calculation results also support our theory. That is, these two resonant modes are independent from each other. So we can use two resonant frequencies and two quality factors to characterize the parameter we need. In order to confirm that, here we designed a circuit prototype. As you can see, two variable resistors are utilized as the sensitive resistor, and the two voltage-controlled varactors are utilized as the sensing capacitor. And it shows that when Cx is changed, the first resonant frequency is shifted with it, and if Rx is changed, if Rx is changed, the resonant frequency is stable, but the shape of the first peaks is changed, which means that the quality factor of the first mode is changed with Rx. And that is similar for the second resonant mode. So if we can use it to characterize the parameters we need. And this is the calculated frequency and the quality factor from the equations above. Then, if we using a linear fitting, it is easy to get the two expressions below, from which we can calculate the information about Cx and Rx we need. This is for the first second mode, resonant mode, and this is for the second resonant mode. So the circuit prototype proves that our circuit have a potential to realize 4 parameters monitoring only if we can replace the variable resistors and the capacitance with some real sensing elements. And that is what we are trying to do for our future research. Okay, finally, I want to make a conclusion of this presentation. To overcome the challenge of monitoring multi-parameters monitoring using LC sensors technology, we designed a novel dual resonant circuit who have two different resonant modes can be used to characterize different parameters we are interested. And based on which we designed two parameters dual-resonant sensors, which can be utilized to monitor pressure and humidity at the same time. And the second prototype proves that using the frequency and quality factors together, we can realize 4 parameters monitoring at the same time. And it can provide competent solutions for the LC sensing technology. And what we believe it will be very valuable in many applications. And that's all about my presentation. Thank you for your attention. Thank you.
Thank you.